So, first of all, let us since we are we are doing in this class lots of mathematics and lots of complicated mathematics, and if I say frankly, it's not at all interesting. So let us clear in our mind that what is our motivation, why we are interested in such complicated mathematical theorem after mathematical theorem. So let's first by words I'm going to try to discuss about those things first, then I will. So first of all, so what is our goal? So our goal is to know what is ultimate behavior of a system. Suppose that in suppose that in case of cell division, we want to know that is the cell division of some part of our body are chaotic or not in the near future. What is the ultimate fate of some cell division process? Will it be chaos? Will it become chaotic? And there are lots of paper in Google Scholar which says that and it is actually the since the we both know that the chaos means the unpredictable cell divisions, and its cell division becomes if the cell division become chaotic, then it's look like chaos. So it is very important to know whether our system, whether our cell division will look like chaotic or it will remain in some fixed point, or in some other extent. Suppose there is a population, and that population eventually will go toward extinction or not. If our model, mathematical model, says that it going to extinction, then that species become endangered, and we have to take special care of that species. So there is no way to know future, but through mathematical model we can approximately going towards that goal to know the future. Now that's why we are interested in this mathematical modeling. Now first of all, what we take a system and we try to how much uh, we try to generalize the system in such a way that we can mathematize that thing, and we can approximately mathematically model that system whose fate we are going to study. Now suppose that after getting that equation will look like that. Suppose the density of the cell in a particular area will look like r into xn 1 minus xn. Suppose that we can model through our discrete logistic equation. We can since cell division is kind of making a mother cell making a daughter cell, as it is clone, it is clone of the daughter cell is a clone of the mother cell. So this could be thought as a reproduction of that cell, and it could be well represented through a discrete logistic equation. Now if we get the logistic equation, then so far so good, but what this equation will not tell us the what is the future will look like. So there are two possible ways to know the future or the ultimate fate of the system. So one way is that brute force method. That means you measure the cell density. Suppose you measure the cell density at this time, suppose x0, and apply it and write a code in using by computer, write a code such that x0 will generate x1, and after putting x1 I will get a x2. So this will generate a sequence, and from that sequence, the end of the sequence, I will get some result that will be the future or the fate of the system. Now is it all? Now suppose that does this method of knowing the future tells about if I merely deviate from this x0, means suppose it's not x0 but x0 plus delta x0, where delta x0 is very small, suppose it's close to 0 but it's not 0 but it is close to 0, will that sequence that we have generated from computer tell about anything, that what the orbit will look like if we instead of x0, if we would start from x0 plus delta x0? So there is no guarantee that where this orbit hit, this orbit will also hit the same point. So one of the thing this, and we know if the system is chaotic, then it become horrible, because chaos means the sensitive dependence of the initial conditions. So if the system is chaotic, we can in general say what will be the ultimate fate of the system, because we know that if I shift a little bit, after time t it will become something else which will not follow the same orbit at all. So that's why we need a general thing, a general theorem, a mathematical theorem that will say, or that will from where we can conclude, from that theory we can conclude something which is general, which will not depend on the initial condition. Wherever we have start, wherever, no matter what initial condition we will start, we can safely say the system will behave here like this. So that's where this complicated mathematics is very important, because we can say general, something general about the system. And in this goal, how far we have reached? So in this goal, how far we have reached? So we have seen that if we have some linear map, suppose we have some linear map like this, where if we have some linear map, okay, where it is, if we have some linear map like this, suppose y equal to x, and we know that there are some system which could be mapped by linearly through a linear map, and one of such system is our body temperature regulation. So that could be modeled through a linear map, and that this map will look like that. And we know we mathematically prove the theorem that if a is less than 1, where no matter wherever you start, the system will go to its fixed point, that means, that physically means that our body can regulate the temperature. And if a greater than 1, that will mean that the body can't regulate its temperature. So that's where we have reached. Now in the previous class, what we have learned since previous class, and it is the thing, basically thing is that the most of the natural real system can't be modeled through a linear map. So it means most of the system actually mapped by a non-linear map, non-linear, very complicated looking map. And we know for a non-linear complicated looking map, it is very difficult to see where what is the fate of the system. Now we have asked in the previous class that could we, is there any, could we by anyhow use the linear approximation, which means could we use the linear map, which is very easy to handle, to to show the general behavior of that system? And we have seen that yes, indeed we can approximate the behavior. Why it is happening like this, I don't know. So let me clear it. So so where was I? Yeah. So that's why. So we have learned that yes, indeed, we can closely approximate the map if approximate a map in a point. So yes, we can approximate a nonlinear map, suppose fx, around a point and its close neighborhood by its tangent. So we, yes, indeed, we have succeeded that much that we can approximate the behavior of a map, exactly behavior of a map of a point, of any point and its close neighborhood approximately by the tangent tangent drawn at that point. And we have proved that we can do so from by this lemma. This lemma says that the behavior of the tangent around a point P is very similar to the, means it's approximately exactly, I will not say exactly same as the nonlinear map, but this linear tangent map can be very good approximation, and it is actually excellent approximation in the neighborhood, close neighborhood of P of this nonlinear map. And since we know that if I have a nonlinear map and if this coefficient at that point, suppose P, now if this coefficient is less than 1, we know that the system will go towards that point. Now what is the question? So if the and we know the system will not remain at any point, because under the iteration in the next time, under the iteration of the map, it will shift towards another point. Now is there any point which will not going to anywhere, it will remain fixed under the iteration? Yes, indeed there is, that is called fixed point. Now the question comes that I if I want to see the behavior near about the fixed point, suppose is suppose this, the here is a fixed point, suppose this is a fixed point. If I want to know what is the behavior of the system near about the fixed point, what we will do? We will simply see, since we, if I draw the tangent of that of that nonlinear map in P, we will get a tangent map, and in the tangent map what is the coefficient that will depend its behavior, whether it will, whether or not it will go towards that fixed point or not. It simply says that I have to calculate the first derivative at that point, and if becomes less than 1, then we will say that all the neighborhood initial condition will be attracted towards this fixed point, and if f prime p is greater than 1, then all the neighborhood fixed point will be repelled by the point p. So that's all. That's why, since we can by simply by looking at this derivative, looking at the first derivative, which is very easy to calculate, we can say something general about the system. That's why we are interested in the complicated looking mathematics. Is it clear, Subhusaji? हाँ. Hmm. हाँ. Hmm. 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 Yeah, yeah. There is a paper. I will share the paper, but the nitty gritty of those things will be there. But I will say in general, if I model through a logistic map, you will see that, means I, because we are not in that point that we can mathematically define the chaos, but indeed actually we can say in general when the chaos will come. Means you can see that thing. So I will come that things in this class. So that's all. Now let's see one thing. Means, is it true that the system can only have fixed point? Only have fixed point. It does not show any other possible outcomes. So Busaji, could you tell me that what are the other possible behavior that a system can show, mathematical system can show. Huh. Hmm. Hmm. Huh. Hmm. Huh. Hmm. 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 Yeah, that's true. That's true. Okay, but the system can have another thing that is called oscillatory behavior, or it is called the periodic behavior that we have discussed. But as you said that as we have learned in the previous class, you are right that periodic behavior is nothing but generalize we can generalize the definition of periodic orbit by fixed point. So in this way you are right that the system only compose a fixed stable or unstable fixed point. But how we will see how one can analyze whether the system will go towards a periodic orbit. How does one conclude that the systems eventually go towards hit a periodic orbit or not? Now this is our question. Now in this class I will say this, then we will come to a point where we can discuss something about the chaos. Okay, so this is our question. Now let's go back to our definition of, suppose we want to say a two period orbit. Two period orbit. Now what is the definition of the two period orbit? Subhaji, could you tell me, means if you can recall them, what is the definition of two period orbit? Hmm. Huh. 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 Hmm. Huh. Hmm. Hmm. Yeah. Okay. Yeah, you are right. That means if I apply the function two times f of x in some initial condition, then the state will remain same. Means I have start from department to hostel and hostel to department. I came back to my hostel. I came back to my department. Since department to hostel. So that means this is a example of two period orbit. Yes, you are right. So that means, so under, so x0 is a fixed point, means two period orbit is nothing but x0. If suppose x0 is periodic orbit, then under the f square it will remain fixed. So that means x square is a fixed point of f square function. Now we are came to that point where we can apply our machinery that we have learned here. So we don't know whether the f square means f square is periodic or not. We have reached that much so far. So if I see only x0 is a fixed point f square, now what is the behavior near about x0 of the f square? So what we have to do, we know that if there is a map, suppose let me generally write this map, and then we can apply it. Suppose x0 is a fixed point, so what is the neighborhood behavior of the x0? If f prime x0 less than 1, then x0 will be stable fixed point, and if f prime x0 is greater than 1, means f square, so ddx of f square x at x equal to x0, if it is less than 1, we will say that the x0 is a stable fixed point, and we know from the theorem, that if x this is less than 0, the system will approximately go to x0, and if it is approximately going to x0, then we will say under the map f, not f square, under the map f, the x0 will look like 2 period orbit. So we will see in a computer simulation, so how it will look. So first of all, so that's it. Now let's see whether it's not map. Suppose x is, suppose let's write a map, logistic map. Xn plus 1 is r into xn 1 minus xn. So this means f of x means r x 1 minus x. Now if I apply f of fx, so we know that a function applied on x will look like r, a function applied on fx, r f of x into 1 minus fx. So Busachi, if you did not get any point, you just stop me and ask. R, and this is will be r x 1 minus x, and this will be 1 minus r x 1 minus x. So you see, this is a function f square x is a function of x, which suppose you can, if you want, you can write as a function g of x, and g of x is r square x into 1 minus x into 1 minus r x into 1 minus x. Now we don't know from where this map came. So if one wants to know what is the behavior of this map near about the fixed point, whether this will go towards a fixed point or it will diverge from the fixed point. Let's see it, then it will be clearer. Suppose this is our map, cool and good. Suppose fixed our parameter r equal to 3.2, maybe I can 2 or 1, whatever you want. Suppose r equal to 3.2. So terminal, so let's first see the behavior. Oh. Okay, let's see the, okay, what is the parameter? Let me check. Parameter is, we started, what is the parameter value? Parameter is 3.2. okay, then let me regenerate. So it's a cobweb diagram of that this map. Fx equal to, you can see that fx equal to r x into 1 minus x. So you can see the cobweb diagram, and the initial point I have started, it is 0.07. So you will see that this orbit will closely become periodic. So if you see, so it's eventually hit the periodic orbit. Now it is not going to some fixed point. Means in case of, we have seen in case of, so if I write it here, in case of 3.2, if my r, this parameter, become 2, you will see that it will hit a fixed point. So if in case of this, you will see that it remains there, it actually hitting a fixed point. But for 3.2, it the behaves not same as it behaves previously. So there is a behavior, it is called orbit or periodic orbit. So you can see that it eventually hit towards a periodic point where it oscillates between 2 points. So here you can see, here you can say like that one is my department, another is my hostel. So it's oscillating between my department and hostel, department and hostel. So this kind of behavior. Now the question that was I asked, that how can I know that this the system, if I start, if means initially if I don't have knowledge and if I don't have computer, so how can I know that the system will behave like this? So for that, what we will see, so one method is that check the stability of this map gx equal to r square x 1 minus fx at 3.2. So let's see what are the fixed point of this map. So what are the fixed point of map? So we know that to solve the map I have to solve this equation, r square x 1 minus x and 1 minus r x 1 minus x. So this is a very complicated looking map. So I used another computer program to solve this equation. So clear. Now first of all, using that let's so I will show you, just give me a moment. Then also first let us see whether or not fx, means under the map fx there is any stable fixed point or not. That list we have to check. So let us first calculate. So what we have seen one thing, the system has a two period orbit, that we have seen. So first what we will check, that whether or not fx has any fixed point, and if it has, then why not it is going to the fixed point. So that means if it is not going to the fixed point, as we have seen in the computer program, that it is the case that it is not going to the fixed point, that means the fixed point become unstable. So let's check that first. So fx equal to 3.2 x into 1 minus x. So that means fixed point means we have to solve this equation, x equal to 3.2 x into 1 minus x. So 3.2 x 1 minus x equal to 0. So here x 3.2 1 minus x minus 1 will be 0. So that means x equal to 0, or 3.2 1 minus x equal to 1, and it will become that 1 minus x equal to 1 by 3.2. So x will be 1 minus 1, 3.2. So it is 3.2 minus 1, so 22 by 32, so 11 by 16. So this is the thing. Now let's check one by one whether this point is stable or not. Let us check stability. Stability means if I start initially around x equal to 0, it will go towards x equal to 0, or it will go further away from x equal to 0. Let us check that. So we know that our machineries we have to check what is the f dash x, and if I calculate f dash x near 0, we know that whether or not it will go towards x equal to 0 or not. So f prime x is 3.2 into x minus x square, that is our fx, and if I derivative it, so 3.2 d dx of x minus x square, so this will be 3.2 and 1 minus 2x. Now let us check f prime 0 at x equal to 0, what it will be? It will be 3.2 simply, and it is greater than 1, and if it is greater than 1, from our theorem we know that x, the point, if I start from neighborhood or x equal to 0, so if I start from neighborhood x equal to 0, here suppose x 0, our system will always diverge, or the x equal to 0 always repel the x 0, and it will x 0 under the iteration of f, the x 0 will become further away from x equal to 0. That we have proved by theorem. Now that is not the case. Now let's see, maybe this is stable. Let's see that. So f prime of 11 by 16, so 3.2 into 1 minus 2 into 11 by 16, so 3.2 into, this is 8 minus 11 by 8, 3.2 into, this is minus 3 by 8, so it will be 0.4, and it will, you see, this is minus 1.2, and it is negative, but f prime, what is the magnitude value? 11 16, it is 1.2, and it's also greater than 1. That means under the map f there are two fixed points. Yes, we have got the question, answer of the question, the first question, that is, yet there is there are two fixed points, one is x equal to 0 and one is x equal to 11 by 12. But unfortunately or fortunately, whatever you see, that if I start from any neighborhood of x equal to 0 or x equal to 11 by 16, the initial condition of the system's state will not remain there, it will repel by the two fixed points. Now the question comes, what happens to the system, where the system will go? Now we have seen by from the computer simulation, it goes to a 2-period orbit. Then we start to looking at the thing that whether or not f square has any fixed point. If x square has any fixed point, if x square has any fixed point, if there is a solution of x0 for this equation, we know that f square has a solution, and if f square has a solution, we know. So then what we will do in the third step, what we will do, we will ask the question, does f square has any fixed point or not? If f square has a fixed point, then we will say, if it exists, then we can say the system has a 2-periodic orbit. Let's check that. So to check that, since we calculate the f square x, which looks very complicated, so that's why we are going to use a computer programming to solve it. Okay, where my cubic, I think it's a cubic root. Let's check. Here is the mu value is 3.2. Let's check the solution. 3 cube. Yeah, so we get, okay, what we have got. So this is, if you can see, this is the 4 fixed point of this so if you see, this is a fourth, the root, if you see, there are 1x 2 3 4, so it's a cubic, it's not cubic, it's the order of the x is 4, so there are 4 solutions exist, and the 4 solution is, first is x equal to 0, second is this, and third one is same as, third one is, if you can calculate, the third one is 11 by 16, it's nothing but by 11 by 16. So we have checked why, and we know that any 1-period orbit could be a 2-periodic orbit as well, because if one point, so let's check that. Suppose it's since the from the definition, if one, suppose x0 is one period orbit, means a fixed point, that means x0 will remain fixed under this map. Now if I apply another f, it will again remain fixed. So x0 is trivially a solution, so that we will not consider, and this, so that means these 2 points we will not consider, and so that means these 2 points will not consider. So let's see there are any other point or not. Oh, here also there is one point, so 0.5130, this point and these 2 points, these 2 points, so that means there exist other than these 2 points another 2 points, so we can say in general, yes indeed. So in yes, the answer to the question is yes, there exist. One is 0.53 and another is 0.799 or 0.799. So there are 2 points. Now let's check whether these two fixed points of f square are stable or not. And to do that, first of let's do that. So so if to check that, we have to check what is the derivative t dx of f of x. Now if you know a little bit of differential equation, so this will be, so I can make it d of f of x, and another d of f of x and d of x. Now let's, for this case, let's see f of x equal to y, so this means d of f of y dy into d of f of x dx. So that means f prime y and f prime x, and y means f prime of f of x. So if the system has a two period orbit, suppose x0 and x1, suppose x0 is 0.513 and x1 is 0.799, we know under the map f x0 it will go to a point x1. So suppose we want to check the stability of x0, so suppose we want to check the stability f of x at x equal to x0, then we know that f prime of f of x0 and to f of x0, so this means f prime of x1 into f prime of x0. So, and we know that what is the f prime, we know the f prime is 3.2 into 1 minus 2x, so 3.2 into 1 minus 2x1 into 3.2 into 1 minus 2x0. So let's put it there. So 1 minus 2 into 0.513 into 3.2 into 1 minus 2 into, this is 1 is 0.799. Let's calculate it. Let's use a calculator and calculate it. 3.2 into, okay, let's use this calculator by Google. Or if you has any calculator, you can calculate and tell me what is the answer. 3.2 into 1 1 into 0.51513 bracket into 3.2 into bracket 1 minus 2 0.799. Yeah, we got the answer. It's very difficult for me calculating, but okay, it's near about 0.15, 0.159. So, or 0.159, you can write it 0.159. And you can see why I am excited, because you know that this d of f square x is less than 1. So that means d dx of f square x at x equal to x0 is less than 1. That means this fixed point is stable. So you see, the under the f square x, if the f square x has a fixed point x0, and this means the under the f square, the x0 is a stable fixed point. So if I start any near about anything, it will go towards the fixed point. So let's check it. So let's check it from this computer program. Okay, let's generate a cobweb diagram which is not for, this is fx. Okay, so we know how to do it. So r into fx into bracket 1 minus of minus of this. Okay, 1 minus of r into x, this is the thing. Okay, not here, sorry, let's put it here. Let's Python 3 cob you see that this is approaching toward a fixed point which is x0, and previously we have seen that these the system actually oscillating between this point. So if you see the what is this point, this is 0.799. So what we have say, what I have said, that it x0 is a stable fixed point. Now I started, let's make it from point 0.4 to 0.85. Let's make it, then it will be clearer and it is easy to see. 0.41 to 2.82. Okay, let me, will it work or not, I don't know, but let try me. Okay, this is not working, no problem. Okay, yes, it is working. So you can see that my initial condition 0.70 is going towards the fixed point x0. Now this is the fixed point. If you can see, this is the fixed point corresponding to 11/16, and another fixed point is 0, that I know. This is corresponding to 11 by 16 fixed point. This is 0.799 and this should be 0.513. You see 0.513. This is 0.513. This is 0.513. Now if I start from here, suppose 0.68, suppose 0.68, or if I start my initial condition not 0.70 but 0.65, maybe 0.68, maybe 68, maybe, then you see that it will come towards the fixed point 0.513. It will generally come, asymptotically come towards the fixed point. This is the thing. So now this is the thing, and the same thing if I want to see under this map, okay, under the map f of x, this is my f of x, this is my f of x. The same thing if I see under the f of x, you will see that the two periodic orbit. It is not clear here. Or maybe you can hear it's clear. So around that, this is the fixed point, this is the unstable fixed point, that is 11 by 16. So you will see that there is it will eventually go towards a periodic point. Okay, now you see this is a two periodic orbit. So that I am saying that is one way to see mathematically what is the behavior. So under the f, it is looks whatever looks periodic under the f square, it is a stable fixed point. So to check whether or not there is two periodic orbit, if suppose you got that the a under the f, the all the fixed point become unstable, then there is a possibility that the system may contain some periodic orbit. So you have to check what periodic orbit it does contain. So you first check f square, then you check f3, say does it 3 periodic orbit, does it 4 periodic orbit. So that's how you will see the in general stability. So is it clear, Subusari? Okay, then now the thing I will come to, that thing is that will be main thing. Now from here, how we will know the some glimpse of chaos. Suppose same map, suppose xn plus 1 is r xn 1 minus xn. Now somehow you see that fxx is r xn 1 minus xn. Suppose this is a behavior of some, you are wanting to measure the cell density around some part of your some body, and that density is in normalized form, suppose xn. You are measuring it after every, I don't know, means I actually don't know what is the time scale of the cell division, but let's assume that you are observing after every 1 minute. Now after every 1 minute you observing, and you find that this kind of equation they are following, and you will see after, means r is nothing but what is the growth rate. We know that from our and in the beginning of the class we know that what does r is equal to basically 1 plus mu, where mu is the just reproduction rate, and in 1 minute how much they will reproduce, in how here also in 1 minute how much they will, thus one cell divided into how many cells. So that's all. Now you see that when I increases r, we know that if r equal to 2, for r equal to 2, so let's generally r equal to 2, let's calculate the stability at r equal to 2. So what is f prime f0 at r equal to 2? The 2 into 1 minus 0 to 2, so that will be greater than 0. Okay, that will be greater than not greater than 0, I am sorry, there is greater than 1. So at r equal to 2, the f prime means 0 is not stable. F prime, suppose another fixed point will be half, I know that, so that's why half into 2 into half into half. So don't worry. So let's do it in a manner where anyone can understand. So let's first solve the equations. Fixed point for r equal to half, that will be x into 1 minus x. So one solution is x minus half into x 1 minus x, that is 0. So one is x equal to 0, or 1 minus half into x minus 1, oh sorry, 1 minus x will be 0. So that will be 1 minus x will be 1 minus x will be 1 minus, so 1 minus x will be, oh sorry, this is not half, this is 2, actually this is 2. R equal to 2, I am wanting to solve this equation for r equal to 2. So 2, so this is half, so x will be half. So there are two fixed points, and if I want to check the stability at f prime x, we know that that is basically 2 into 1 minus 2x from our previous calculation. So at x equal to 0, it will be 2, which is greater than 1, that means x equal to 0 is unstable. No system, no initial condition will go towards x equal to 0. On the other hand, f equal to 0, x equal to half, you will find that 2 into 1 minus 2x is 2 into 1 minus 2 into half. So this is 2 into 1 minus 1 means 0, means equal to 0, that is again less than 1. And you see, if you draw the curve diagram for x r equal to 2, you will find that x equal to half will be stable fixed point. All initial condition will go towards x equal to half. So from there we know when r equal to 2, it fx has a stable solution. Now we know that what we know that for r equal to 2, we know for r equal to 2, we know that the fx has a stable solution, which is half. The system will go towards half. Now another thing we know, if I increase the r further, r equal to 3 by 2, you will see that fx will not have any fixed point, any stable fixed point. That we have checked, that there are two fixed points, stable fixed point, one is 0, and there are two fixed points, one is 0, another is 11 by 16, both of the fixed point. So there are four fixed point, there are four fixed point exist. One is x equal to 0, one is 0.513, one is 11 by 16, another is 0.799. And we have checked that under the fx, these two fixed points are unstable. Okay, these are the fixed point for, okay, sorry, these are the, so these are the two, okay, sorry, so these and these fixed point 11 by 16, and we have seen that these two fixed point are unstable. When I increase the r, means if I increase the reproduction rate, or if I increase the rate of cell division, then the cell density will not remain constant at half, suppose not half but something, it will not remain constant, but it will be oscillating between something if I increase my reproduction rate further from 2 to 3.2. And you see this become unstable, and what will become stable? F square x has two stable fixed point, one is x0, one that is 0.513, another is 0.799. So these two fixed point are stable under the f square, and under f it will look that the system will oscillating between 2 points. Now if I increase furthermore, and so if I increase r, what happens? So the stability of the fixed point has changed. So if we decrease, suppose r equal to suppose 1 or something, if you take r equal to 0.5 or something else, you find that fx has two fixed point, 0 and another thing, but you see that fx has a stable fixed point which is 0, so it will going to extinction. Now when I increase the r further, you find that the other fixed point, that half, will be stable, and 0 become unstable. Now if I increase r further 3.2, you find that the both of the fixed point become unstable. Now what becomes stable? That fixed point of f square x, that means it become oscillatory. Now these suggest us that if I keep increasing r, now if I keep increasing r, means if I keep increasing the rate of cell division or rate of reproduction, what happens? Now at some point the two fixed point of f square x also become unstable. So in the similar pattern, are you agree or not, Subhusaji, here, that if I increase r, the fixed point of f square x, two fixed point of x square x, stable fixed point, also become unstable? Huh. Huh. Now then what we will check? We will check f3, and you see that fq will not exist in lower limit, but you check fq. Now fq, after some point fq will remain fixed, and then it will become unstable. Now you will find a point, so it's near about r equal to 4, and it is called the onset of chaos. It is called onset of chaos. Onset of chaos. You will find that the all fixed points are unstable. It means the fixed point of fx, fixed point of f square x, fixed point of fqx, fixed point of f4x, fixed point of f5x, all fixed points exist. These are nothing but the periodic orbit. This is periodic orbit, this is periodic orbit, this is periodic orbit, this is periodic orbit. All the fixed points, all the fixed points of f square, fq, f4, this is 2 period orbit, this is 3 period orbit, this is 4 period orbit, this is 5 period orbit, this is 6 period orbit, all the periodic orbits become unstable. Then what happens to the system? You see that there exists no stable fixed point for fx, no stable orbit, no stable 2 orbit, no stable 3 orbit, no stable 4 orbit. Then you will see that the system will become chaotic. Then you will see the chaos will emerge, and you will see the system will be chaotic, because there is no stable attractor at all, and the fixed point will be roaming around all the phase space. And every fixed point, why it is happening? Because we know that whenever it will come close to any fixed point, since that fixed point is unstable, what it will do? It will repel the initial condition. When it will repel the initial condition, it will go near to another fixed point, suppose period 2 fixed point, means in close to period 2 orbit, and since period 2 of period orbit also unstable, it also give a repel to that point, and it will go somewhere else, and every fixed point, every fixed point since become unstable, every fixed point will repel that initial that condition, that system state. That's why it will roaming around chaotically on the phase space. On the phase space, that is chaos. So that is here, and in the context of cancer, you can say me means you can say me very means I don't know exactly. You can say me exactly what it is, but I know that if the cell rate of cell division become larger, r equal to 4 means become larger, the cell division become larger. If cell division become larger, then chaotic thing means in the cell division it become cancerous. So the cancer will emerge. As the chaos will emerge, the system will be unpredictable and chaotic, and since the rate of the cell division become higher and chaos is there, the cell can divide here to here and here to there. So that's the thing. That's how you can relate the chaos to the cancer. So is there any question, Subhusachi? Because I don't know exact nitty-gritty of those cell division process. I only know that if somehow by genetic mutation or something you can uh, you can uh, you can make their proliferation rate higher, that r become greater than something, that rate of division become higher, then it can be the case, it could be the case that particular part of the body would has a cancerous cell. So that's all for. Yeah, yeah. Hmm. 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 Ah. Ah, great. Congratulations. Congratulations. Okay. Hmm. 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 No, no, you see things. There is a simple difference. You are right. You are just confused about the fixed point and stable fixed point. The fixed point is attracting or not. They remain fixed point. Yes, indeed they remain fixed point. But in the case, if you start from the fixed point, you will remain there means for eternity. But what is happening here, that fixed point is attracting towards other initial condition or not. So if some initial condition get close to that, it will not become more closer to the fixed point. What that fixed point will do, suppose it you can see like this example. So suppose you are in a top of a hill, in a top of a hill. If you reach to the top of a hill, means if you put a ball there, it will remain fixed there. But if you just part up the ball slightly, it will not stay there, it will fall apart. So that kind of fixed point it becomes. And what the stable fixed point means, it is the bottom of the hill. So when in the in some valley, in the bottom of the valley or in the mountain valley, what if you put some ball there, if you part up a little bit the ball, it will come down again to the same point where it has been started. So that is the difference between the stable fixed point. So bottom of a hill, if I put a ball, that bottom of a hill is a stable fixed point, and the top of a hill is kind of like a unstable fixed point. So here, whose those fixed point attracting, those are kind of bottom of a hill kind of thing. Is it clear? Huh. Uh, yeah. Okay. Thank you for joining the class. Okay, I'm quitting this class.